November 8, 1942, Richmond, California. Henry J. Kaiser's foreman watched arc welders shower sparks across the night-blackened shipyard as the clock struck 1 minute past midnight. This has to be impossible. 250,000 parts, 14 million pounds of steel, 4 days to assemble a 441-foot cargo ship capable of crossing the Pacific Ocean. The Richmond Shipyard No. 2 stretched across the waterfront, illuminated by thousands of work lights, transforming night into artificial day. Prefabricated hull sections, each weighing 30 tons, sat positioned on railroad flat cars, arranged in precise sequence around the empty ways. Deckhouses stood complete in assembly areas. Engine components gleamed with fresh oil. The keel plates waited suspended from cranes, ready to drop into place the instant midnight passed. This was not standard shipbuilding. This was something the maritime world had never attempted. At 12:01 a.m., the first keel section, serial number 763, yard number 440, settled onto the building ways with a metallic thunder that echoed across San Francisco Bay. Workers swarmed the steel like ants colonizing fresh territory. The SS Robert E. Peary had begun her journey from concept to completion. Kaiser had made a promise to President Franklin D. Roosevelt: prove America could build ships faster than Germany could sink them. 4 days. That was the deadline. The stakes extended far beyond one ship. In the frigid waters of the North Atlantic, German U-boats prowled convoy routes with methodical efficiency. Their strategy was mathematically simple: sink merchant ships faster than the Allies could replace them. Britain would starve. The Soviet Union would collapse without American supplies. The war would end in Axis victory through strangulation of supply lines. In 1941 and 1942 alone, German submarines and surface raiders sent 2,963 Allied merchant ships to the bottom, more than 3 times the 863 replacement vessels American shipyards managed to produce. Every torpedo that struck home pushed the Axis closer to victory. Every day that passed without adequate replacement tonnage meant fewer tons of ammunition, food, fuel, and equipment reaching the fighting fronts. German naval intelligence had calculated the equation precisely. At current loss rates, Allied merchant capacity would reach critical shortage by mid-1943. They had no idea American industry was about to transform that calculation into meaningless optimism. The journey to this midnight assembly line had begun 4 years earlier, when Britain stood alone against Nazi Germany. September 27, 1940, London. The British Ministry of War Transport faced catastrophic merchant ship losses. German U-boats and Luftwaffe bombers were destroying cargo vessels faster than British shipyards. Many damaged by German bombing raids could replace them. Britain needed a simple, fast-to-build emergency cargo ship design. Naval architects at J.L. Thompson & Sons in Sunderland modified an 1879 British tramp steamer design, creating specifications for what they designated the Ocean Class, 441 feet long, capable of carrying 10,800 deadweight tons, powered by a 2,500 horsepower triple expansion steam engine, producing 11 knots maximum speed. The design prioritized one factor above all others: speed of construction. Simplicity meant survival. Standardization meant production volume. Britain placed orders for 60 Ocean-class vessels, but British shipyards lacked capacity to build them quickly enough. The ministry approached the Maritime Commission with a desperate request: could American shipyards build these emergency cargo ships? The U.S. agreed, and on January 3, 1941, 11 months before Pearl Harbor, the Maritime Commission adapted the British ocean design into what they designated the EC-2SC-1, Emergency Cargo 400 to 450 feet length class steam engine design variant C1. President Roosevelt attended the launch of the first 14 EC-2 vessels on September 27, 1941, at Baltimore's Bethlehem Fairfield shipyard. Roosevelt christened the lead ship Patrick Henry, invoking the Revolutionaries' Declaration, "Give me liberty or give me death." The ships became Liberty ships, a public relations masterstroke that transformed ugly ducklings into symbols of American determination. The first Liberty ship took 230 days to build using traditional, riveted construction. That timeline was militarily worthless. At that pace, U-boats would win the tonnage war by simple mathematics. American shipbuilders needed revolutionary changes in both technique and mindset. Henry Kaiser provided both. The industrialist had built the Hoover Dam, Grand Coulee Dam, and Bonneville Dam, massive construction projects completed ahead of schedule through innovative techniques. Kaiser had no shipbuilding experience. That proved to be his greatest advantage. He approached shipbuilding not as a centuries-old craft, but as an assembly problem identical to constructing dams. Prefabricate components, move them to the assembly site, join them rapidly using the fastest method available. Kaiser's revolutionary insight: replace riveting with welding. Traditional riveted construction required teams of skilled riveters heating metal rivets to glowing temperature, inserting them through aligned holes, then hammering the rivet ends into mushroom shapes to secure the connection. Each rivet required multiple workers, significant time, and considerable skill. A medium merchant ship contained 3 million rivets, weighing 300 tons, representing thousands of man-hours of skilled labor. Welding eliminated all of that. Electric arc welding fused steel plates directly, creating seams as strong as the surrounding metal. Welding required less skill to teach, could be performed by a single worker, and proceeded 5 times faster than riveting. The weight savings alone, 300 tons of rivets replaced by perhaps 30 tons of welding rod, increased cargo capacity significantly. Kaiser opened his first Richmond shipyard on December 14, 1940. The yard launched its first Liberty ship, the SS Ocean Vanguard, on October 15, 1941, 197 days after keel laying. Not revolutionary, but Kaiser was learning. His yards began employing Ford Motor Company assembly line principles. Prefabricated sections, complete with plumbing, wiring, and fixtures, arrived by rail from suppliers across America. Workers assembled these sections like children building with blocks, welding them into complete ships. Construction time dropped rapidly. By mid-1942, Kaiser's Richmond yards averaged 45 days per ship, then 42 days, then 38 days. Each Liberty ship cost approximately $1.8 million, cheap enough that if a vessel made just one successful cargo delivery, it paid for itself. But Kaiser wanted more than efficiency. He wanted to prove American capability so dramatically that German strategists would despair. In September 1942, Kaiser's Oregon Shipbuilding Corporation built the Liberty ship Joseph N. Teal in just 10 days. A reporter asked Kaiser if it could have been done faster. Kaiser replied it could have been built in 8 days, but construction was deliberately slowed to allow President Roosevelt to attend the launch. Roosevelt took the challenge seriously. On November 7, 1942, he sent a telegram to Kaiser: "Can you build a Liberty ship in 1 week?" Kaiser promised better than that: 4 days. The November midnight assembly of the SS Robert E. Peary represented the culmination of months of preparation and years of industrial learning. Kaiser's Richmond Shipyard No. 2 had built 46 Liberty ships before the Peary. Every ship taught lessons. Workers developed techniques for positioning whole sections with millimeter precision. Welders learned optimal bead patterns for maximum strength with minimum time. Crane operators choreographed lifts with ballet-like precision. The entire yard became a living organism whose sole purpose was transforming steel into ships. For the Peary attempt, Kaiser pre-positioned everything. Whole sections fabricated weeks earlier sat on flat cars precisely located beside the building ways. Deck houses stood complete, requiring only crane lifts and welding to secure them. Engine room components waited in assembly jigs. Electrical systems, plumbing, ventilation ducts, every component that could be built ahead was built ahead. The workforce expanded to match the challenge. Richmond Shipyard No. 2 employed 7,000 workers across 3 shifts. For the Peary sprint, all shifts worked simultaneously. The shipyard became a 24-hour operation, with workers covering every available square foot of the building ways. They worked with astonishing coordination. At 12:01 a.m. on November 8th, keel plates dropped into position. By 2 a.m., the first frame sections were being welded to the keel. By 6 a.m., 4 complete bottom hull sections had been positioned and secured. The ship rose from the ways with visible speed, growing vertically as workers added layer upon layer of prefabricated steel. November 8th passed in a blur of arc weld flashes and crane movements. Bottom hull complete, side plates installed, bulkheads secured. The ship took recognizable form, 441 feet of steel stretching down the ways toward the water. November 9th brought the deckhouse installations, prefabricated bridge structure, complete with navigation equipment and radio gear, lowered into position in a single crane operation weighing 45 tons. Workers secured it with continuous weld beads. Engine room components, boiler, condenser, reduction gears, propeller shaft, arrived as complete assemblies requiring only connection and securing. November 10th saw interior work accelerate. Electrical crews strung wiring through pre-installed conduits. Plumbers connected steam lines, freshwater systems, bilge pumps. Carpenters installed crew quarters fixtures, bunks, lockers, tables. The ship transformed from steel skeleton to functional vessel. November 11th brought finishing work at frantic pace, cargo boom installation, lifeboat davit mounting, navigation light wiring, anchor windlass testing, fresh paint, gray hull, white superstructure, ship's name stenciled across the bow in foot-high letters, SS Robert E. Peary. At 4:16 p.m. on November 12th, 1942, 4 days, 15 hours, and 29 minutes after midnight November 8th, shipyard whistles screamed across Richmond. The SS Robert E. Peary rolled down the greased ways into San Francisco Bay, displacing 14,257 tons of water as a complete, functional cargo vessel ready for sea trials. Newsreel cameras captured the moment. Reporters crowded the waterfront. Kaiser had delivered on his promise. America had built a complete ocean-going cargo ship in less time than most people spent on a single work week. The Peary was deliberately termed a stunt ship by critics, who noted correctly that such extreme speed wasn't sustainable for routine production. Kaiser called it an incentive ship, proof of what American industrial coordination could achieve. The distinction mattered less than the demonstration itself. American shipyards had mastered mass production techniques so thoroughly that building ships had become faster than destroying them. But the record-breaking construction of the SS Robert E. Peary was propaganda as much as industrial achievement, and German strategists understood that distinction clearly. The real transformation in the Battle of the Atlantic came not from single sprint-built ships, but from sustained production volume. By mid-1942, the cumulative learning from hundreds of Liberty ships built across 18 American shipyards began generating dramatic results. Average construction time across all yards dropped from 230 days in early 1941 to 42 days by September 1942. Then production volume accelerated further. In January 1943, American shipyards launched 140 new merchant vessels. In February, 150. In March, 162. By spring 1943, 3 Liberty ships were splashing into American waters every single day. More than 20 per week. More than 90 per month. The construction rate exceeded even Kaiser's optimistic projections. German U-boat commanders began reporting an impossible situation. In March 1943, Gross Admiral Karl Donitz's submarines sank 108 Allied merchant ships in the North Atlantic, a devastating toll representing 627,377 tons of shipping. Under previous calculations, such losses should have created critical shortages. Instead, Allied convoys grew larger. More ships meant more escorts could be assigned to protect each convoy. More ships meant losing 15 vessels in a single convoy still left 30 arriving successfully. The mathematics had reversed. In 1941 and 1942, German submarines sank 2,963 Allied ships, while America built only 863 replacements, a catastrophic deficit of 21 vendored vessels. But by 1943, American production alone was building 15 Liberty ships annually, while German U-boats sank approximately 1,000 Allied merchant vessels total, and not all were new construction. The surplus began accumulating. Every month, Allied merchant capacity grew rather than shrank. U-boat ace corvette Captain Otto Kretschmer, captured in 1941, later described the realization that filtered through German naval intelligence. We believed initially that if we could maintain losses above construction rates, Britain would capitulate from starvation. By 1943, we understood our calculations were obsolete. The Americans were building ships faster than we could sink them, even if we sank 3 every day. The tonnage war was lost not because our submarines failed, but because American industry succeeded. The Liberty ship production explosion demonstrated capabilities German strategists had not considered possible. Donitz calculated U-boat effectiveness based on pre-war shipbuilding rates, when constructing a 10,000-ton merchant vessel required 8 to 12 months. American yards reduced that timeline to 6 weeks. German naval planning depended on static industrial capacity, the assumption that yards could build only what they had built before, perhaps with modest efficiency improvements. They did not account for American ability to create entirely new shipyards from vacant waterfront in months. Between 1941 and 1945, the United States built or expanded 18 major shipyards dedicated to Liberty ship production. Richmond alone grew from empty waterfront to 4 massive yards employing 90,000 workers. These were not traditional shipyards accumulated over decades. They were industrial facilities designed specifically for one purpose: mass-producing identical cargo vessels using assembly line techniques. The workforce transformation was equally dramatic. Liberty shipyards employed 1.8 million Americans during the war, many with no shipbuilding experience. Women constituted 30% of shipyard workers by late 1942. African Americans held positions traditionally reserved for whites in pre-war yards. Eastine Koner, a former waitress, learned welding in a 6-week training program and worked as a scaler on the Liberty ship SS George Washington Carver. Josie Lucille Owens trained as a welder trainee in 1943 and contributed to building multiple Liberty ships. Welding made this workforce transition possible. Riveting required years of apprenticeship and significant upper body strength. Welding could be taught to competent workers in weeks and required steady hands more than raw strength, characteristics available in the expanded wartime workforce. The technological choice to weld rather than rivet enabled the social transformation that built the ships. By June 1943, the Battle of the Atlantic had turned decisively. Improved Allied anti-submarine tactics combined with overwhelming merchant vessel numbers to break the U-boat threat. German submarines still prowled the Atlantic, but they could no longer inflict losses faster than American yards replaced them. Donitz withdrew U-boats from the North Atlantic convoy routes in May 1943, acknowledging defeat in the tonnage war. The SS Robert E. Peary, the Sprint-built propaganda ship, sailed through this transformed naval environment on her war service. But her own combat record would demonstrate that Liberty ships were far more than cargo carriers. The Liberty ship design embodied emergency compromise, a vessel built to minimum acceptable standards because perfection took time the Allies did not have. The Maritime Commission issued specifications on January 20, 1941 that prioritized 5 requirements above all others. Cargo capacity, 10,800 deadweight tons minimum, sufficient to transport 440 Sherman tanks, 2,840 jeeps, or 230 million rounds of .30 caliber ammunition in a single voyage. Range, 17,000 nautical miles at 11 knots cruising speed, enough to steam from Baltimore to Murmansk without refueling. Simplicity, components must be standardized across all builders. Every Liberty ship must be functionally identical to every other, allowing crews to transfer between vessels without retraining. Speed of construction. Design must minimize skilled labor requirements and maximize use of prefabricated components. Cost. Total vessel cost must not exceed $2 million, cheap enough for massive production, expensive enough to incorporate minimum acceptable quality. The mathematics were brutally simple. To achieve 17,000-mile range, the ships required 5,700 tons of fuel oil in bunker tanks. To accommodate 10,800 tons of cargo plus fuel, the whole required displacement tonnage of approximately 14,257 tons. To achieve even 11 knot speed with that displacement required 2,500 horsepower from the steam engine. That engine required a boiler producing 240 pounds per square inch steam pressure at 440 degrees Fahrenheit temperature. These requirements existed in direct opposition. Greater cargo capacity meant larger hull, meant greater displacement, meant more engine power required, meant heavier engine, meant less cargo capacity. Naval architects balanced these competing demands by accepting the minimum acceptable value for each. 11 knots was slow but adequate. 10,800 tons was enough. 441 feet was short enough to build rapidly but long enough to avoid excessive rolling in Atlantic swells. The design included deliberate compromises that sacrificed ideal performance for construction speed. The whole form was slab-sided and blunt, ugly but simple to build. The steam engine was a reciprocating triple expansion design from the 1890s rather than modern turbines. Obsolete but reliable and manufacturable by companies with no turbine experience. The bridge and deck houses used rectangular shapes and right-angle corners, stress concentrators, but fast to fabricate and assemble. Naval architect Theodore E. Ferris designed the final American adaptation of the British Ocean class. His specifications called for welded construction throughout, except at stress-critical locations where riveting would provide crack-stopping redundancy. This proved to be an insufficient precaution. The steel itself represented another compromise. Liberty ships used carbon steel, meeting minimum commercial specifications for ship plate, 0.18 to 0.23% carbon content, 0.6 to 0.9% manganese, less than 0.05% phosphorus and sulfur. These were standard maritime steels used in countless pre-war vessels without problems. But those pre-war vessels were riveted. The riveting process itself provided crack-stopping joints. Each rivet hole created a boundary between steel plates. Cracks propagating through one plate could not easily jump the rivet joint to the adjacent plate. Riveted ships could suffer localized damage without catastrophic failure. Welded ships eliminated those boundaries. In an all-welded hull, steel plates fused into a single continuous structure. A crack starting at one location could propagate unimpeded across hundreds of feet of hull. The design provided for crack arrestor straps, reinforcing bands welded across stress points, but early Liberty ships used these sparingly to save construction time and weight. The Liberty ship specifications reflected a calculated gamble, accept compromises in individual vessel quality to achieve overwhelming fleet quantity, build ships fast enough and cheap enough that losing a percentage to design flaws remained acceptable compared to not having ships at all. That gamble paid off strategically, but the price was measured in ships that split in half without warning. January 16, 1943, Portland, Oregon. The Liberty ship SS Schenectady completed successful sea trials and returned to port in calm, cold weather, water temperature 39 degrees Fahrenheit. At approximately 8:45 p.m., workers on the deck heard a sound like a rifle shot echoing across the harbor. The Schenectady's deck fractured just aft the bridge superstructure. The crack propagated instantaneously down both port and starboard sides to the bilge, completely around the hull circumference. The ship's midsection rose skyward as her bow and stern sections plunged deeper into the water. The Schenectady broke in two while tied to the dock. No one died. The ship was unmanned except for night watch crew who evacuated safely. But the catastrophic failure sent shockwaves through the Maritime Commission and naval architects worldwide. Ships did not simply split in half for no reason. Something fundamental was wrong. The Schenectady failure was not isolated. On November 24, 1943, the Liberty ship SS John P. Gaines broke in half in the North Pacific, 400 miles southwest of the Aleutian Islands. She sank within minutes. 10 crew members died. Survivors reported hearing a tremendous crack, then watching the bow and stern sections separate and sink while they scrambled into lifeboats. Water temperature 38 degrees Fahrenheit. December 1943. The Liberty ship SS Henry Bacon developed a complete fracture across her deck while in calm seas off Iceland. Emergency welding repairs held the ship together long enough to reach port. January 1944. The tanker SS SO Manhattan broke in half off Long Island in heavy weather, water temperature 34 degrees Fahrenheit. Similar failures occurred with increasing frequency through 1944. The pattern was undeniable. Liberty ships were experiencing brittle fractures in cold water. By war's end, approximately 1,500 instances of significant brittle fractures affected Liberty ships and related T2 tankers. 12 vessels broke completely in half without warning. 3 of those 12 were Liberty ships. More than 200 Liberty ships suffered serious structural cracks requiring major repairs. Suspicion initially fell on the shipyards and their inexperienced workforce. Critics pointed to rapid construction schedules and women welders as evidence of inadequate quality control. The U.S. Maritime Commission launched investigations examining welding techniques, workforce training, and quality inspection procedures at every Liberty shipyard. Those investigations found problems: welds with inadequate penetration, missed inspections, occasional use of improper welding rod. But nothing systematic enough to explain catastrophic failures across ships built by different yards using different welders. Some of the fractured ships had received extra thorough inspections. The best-built Liberty ships cracked as readily as mediocre examples. The Maritime Commission borrowed the British-built Liberty ship Empire Duke for destructive testing. Naval architects subjected the vessel to stress loads, temperature variations, and metallurgical analysis. The tests revealed something unexpected. The welds themselves were sound. Fractures did not originate in welded joints. They started in the base steel itself, particularly at stress concentration points like hatch corners that Liberty ships used for ease of fabrication. Constance Tipper, a metallurgist at Cambridge University, performed crucial research that identified the actual cause. She tested Liberty ship steel samples using Sharpie impact tests across varying temperatures. Room temperature tests showed the steel had good toughness. It absorbed energy and deformed extensively before fracturing. But when Tipper tested the same steel at 32 degrees Fahrenheit and below, the behavior changed dramatically. The steel became brittle, fracturing suddenly with little energy absorption. Tipper discovered the steel exhibited a ductile to brittle transition at specific temperatures. Below this transition temperature, the steel's crystalline structure changed behavior. Instead of absorbing stress through plastic deformation, the crystals fractured
cleanly along crystallographic planes. Cracks propagated at sonic speed once started. The welding process made the problem worse. Welding heated adjacent steel to extreme temperatures, altering the metallurgical structure in the heat-affected zone near each weld. These zones had different grain structures than the base metal. When stress concentrated at corners or notches, particularly the square hatch corners that Liberty ships used for ease of fabrication, cracks could initiate in the heat-affected zones. Once a crack started in brittle steel, the all-welded construction provided no barriers to propagation. The crack raced along the hull at 2,000 feet per second, limited only by the speed of sound in steel. A crack starting at a forward hatch corner could reach the keel in under 1 second. The ship split before any human reaction was possible. Constance Tipper published her findings and developed the Tipper test for measuring ductile brittle transition temperatures in ship steel. Her work revolutionized understanding of fracture mechanics. But her research came too late for the Liberty ships already built. The Maritime Commission implemented emergency fixes. New Liberty ships built after 1943 received crack arrestor straps, steel reinforcements welded perpendicular to likely crack propagation paths at every deck opening and major stress point. Welding procedures changed to include stress-relieving heat treatments. Steel chemistry specifications were revised to require lower sulfur content and higher manganese, elements that reduced brittleness. These modifications reduced but did not eliminate brittle fracture incidents. Liberty ships continued cracking through 1945, though catastrophic failures became rare. The vessels served adequately in temperate and tropical waters where temperatures didn't trigger brittle behavior. Ships assigned to North Atlantic routes received extra inspections and crack monitoring. The ship SS Robert E. Peary, the 4-day sprint ship, escaped catastrophic brittle fracture. She operated primarily in Pacific waters where temperatures remained above the critical transition point. Her war service proved extensive despite being built as propaganda. The Peary made multiple transatlantic crossings
and participated directly in combat operations. On June 7, 1944, the Peary transported men and equipment from Cardiff, Wales to Omaha Beach, arriving just 1 day after D-Day under constant enemy artillery and air attack. She made multiple shuttle runs to Normandy through September 1944, delivering critical supplies to forces fighting inland from the beaches. Her armed guard crew,
Navy gunners assigned to defend merchant ships, engaged German aircraft multiple times without suffering serious damage. The Peary's Pacific service proved equally demanding. She delivered cargo to Guadalcanal during active combat operations. On one occasion, she rescued American soldiers under enemy fire, taking wounded aboard while Japanese artillery targeted the beach. The Sprint-built ship proved as capable and durable as Liberty ships that took weeks longer to construct. The Liberty ship fleet, despite brittle fracture problems, accomplished its strategic mission. The ships transported 75% of all cargo shipped overseas by the United States during World War II. They carried millions of tons of ammunition, fuel, food, vehicles, aircraft, and raw materials to every combat theater. They transported troops to invasion beaches and evacuated wounded back to hospitals. Some became specialized variants: aircraft transports, hospital ships, repair ships, colliers. 30 Liberty ships were lost to brittle fracture failures, a terrible toll, but 2,710 were built. The survival rate exceeded 98%. From a cold strategic perspective, losing 1 to 2% of vessels to structural failure remained acceptable when the alternative was not having enough ships to win the war. Between 1941 and 1945, 18 American shipyards built 2,710 Liberty ships in multiple variants. Standard EC2S-C1, 2,580 vessels built. The basic cargo carrier, 441 feet long, 56 feet 10 inches beam, 10,920 deadweight tons, 2,500 horsepower triple expansion steam engine, producing 11 knot maximum speed. Cargo capacity 9,146 tons plus deck loads. Range 17,000 nautical miles. Crew of 41 to 50 merchant sailors plus 21 to 40 Navy Armed Guard gunners. EC2S-AW1 colliers, 62 vessels built. Modified to transport coal from Norfolk to European ports. Reinforced holds and improved ventilation systems to reduce coal dust explosions. EC2S-C2-C3 tankers, 24 vessels built. Modified for liquid cargo transport with segregated tanks and pump systems. EC2S-C1-X aircraft transports, 31 vessels built, modified with enlarged forward hatch openings and reinforced deck structures to accommodate assembled aircraft as cargo. EC2S-C5 repair ships, 13 vessels built, extensively modified with machine shops, welding equipment, and spare parts stores to provide at-sea repair capability for damaged vessels. Production peaked in 1943 with 1,500 Liberty ships launched, an average of 4.1 ships per day across all yards. Kaiser's 4 Richmond shipyards produced 747 ships total, representing 27.5% of all Liberty ships built. The Richmond yards held both the lowest average construction time, 42 days, and the fastest single ship record, 4 days, 15 hours, 29 minutes, for the SS Robert E. Peary. Average construction cost per vessel, $1.8 million. Total program cost, approximately $4.9 billion.
At average cost, each Liberty ship required 1 successful cargo voyage to achieve financial break-even. Most made dozens of voyages. Liberty ship casualty statistics: of 2,710 vessels built, approximately 200 were lost to enemy action, torpedoes, bombs, mines, kamikaze attacks, and 30 to structural failures, brittle fractures. An additional 300 to 400 suffered serious damage, requiring major repairs.
Approximately 2,400 Liberty ships survived the war intact. Crew casualties on board Liberty ships totaled approximately 5,600 merchant sailors and Naval Armed Guard personnel killed in action or lost at sea. The per-voyage casualty rate averaged 0.03%, meaning 99.97% of Liberty ship voyages were completed successfully without crew deaths.
For a vessel operating in active combat zones under constant submarine and air attack, this represented remarkable survivability. Comparative analysis reveals the Liberty ship's strategic value through contrast with similar vessels. German equivalent. Germany built no comparable emergency cargo ship program. German merchant fleet totaled approximately 4,000 vessels at war's start, but received no systematic replacement program. By 1945,
German merchant capacity had collapsed to approximately 1,200 operational vessels, most trapped in German-controlled ports by Allied naval supremacy. British equivalent. Britain built approximately 300 Empire-class cargo ships, the original design that inspired Liberty ships, plus various other merchant vessels totaling about 800 ships during the war. The combined Anglo-American merchant construction program produced roughly 3,500 emergency cargo vessels,
vastly exceeding German submarine capability to sink them. Japanese equivalent. Japan built approximately 2,800 merchant vessels during the war to replace losses to American submarine attacks. However, Japanese construction averaged 150 to 200 days per ship, 4 times slower than American Liberty ship production. By 1945, Japan's merchant fleet had been reduced from 6 million tons to less than 1 million tons of operational shipping. American submarines had sunk Japanese merchant vessels faster than Japanese yards could replace them, the exact reverse of the Atlantic situation. The philosophical differences between American and Axis approaches to merchant shipping revealed fundamental strategic thinking. The United States accepted individual ship design compromises to achieve overwhelming numerical superiority. American naval architects prioritized construction speed and workforce expendability over vessel performance optimization. The strategy worked because battles are won by having enough adequate ships rather than a few perfect ones. Germany and Japan both prioritized individual vessel quality over production quantity. They built better ships than Liberty ships, faster, more efficient, better constructed, but they built too few. Quality without quantity failed strategically. The Liberty ship program demonstrated that adequate design mass-produced defeats superior design slowly constructed. American merchant construction outpaced German destruction by 2.5 to 1 ratios. That margin of victory, uncomfortable when translated to 30 ships lost to brittle fractures, represented strategic dominance that ended the Battle of the Atlantic as a threat to Allied victory. The SS Robert E. Peary, the 4-day propaganda ship, served throughout the war without catastrophic failure. She made her final wartime voyage in April 1945, transporting cargo from Boston to Yokohama via the Panama Canal. The route took her across both Atlantic and Pacific Oceans, through waters where dozens of Liberty ships had been torpedoed, bombed, or simply cracked apart in cold seas. The Peary survived them all. After the war, the Peary continued merchant service under private operators. She transported commercial cargo until June 1963, when she was finally scrapped in Baltimore, Maryland, 21 years after her record-breaking 4-day construction, having served longer than many traditionally built ships. The irony was profound. The stunt ship, built as propaganda to prove American industrial capability, outlasted hundreds of Liberty ships that took weeks longer to construct. Speed of construction had no correlation with vessel longevity. The Peary proved as durable as any of her sister ships because she was, in every meaningful way, identical to them. The sprint construction merely compressed the assembly timeline. The quality of materials and workmanship remained constant. The broader Liberty ship fleet served even longer. Approximately 2,400 survived the war intact. Most were sold to commercial shipping companies and continued transporting cargo through the 1950s and 1960s. Some served into the 1970s. 2 survive today as museum ships, the SS John W. Brown in Baltimore and the SS Jeremiah O'Brien in San Francisco, both operational and capable of steaming under their own power. The Liberty ship program's ultimate legacy extends beyond the 2,710 vessels built. The ships themselves were means to an end. They transported 75% of all American wartime cargo, enabling Allied armies to remain supplied and offensive operations to continue. Without Liberty ships, Operation Overlord, the Normandy invasion, could not have been supplied adequately. Without Liberty ships, the Soviet Union might have collapsed under German assault for lack of American equipment and supplies. Without Liberty ships, the Pacific Island hopping campaign would have stalled from supply shortages. The Liberty ship program also revolutionized shipbuilding permanently. Welded construction became standard for all merchant vessels. Prefabrication and modular assembly techniques pioneered for Liberty ships now define modern shipbuilding worldwide. The lessons learned from brittle fracture failures led to improved steel metallurgy, better understanding of fracture mechanics, and design practices that prevent stress concentration. Every modern ship benefits from knowledge, first at the cost of 30 Liberty ships lost to structural failure. The workforce transformation proved equally significant. The 1.8 million Americans employed in Liberty shipyards included unprecedented numbers of women and African Americans in skilled industrial positions. The social changes initiated by wartime necessity continued into peacetime. Kaiser's worker healthcare system evolved into Kaiser Permanente, demonstrating that innovations driven by emergency became permanent social infrastructure. Henry Kaiser's promise to President Roosevelt was simple: prove America could build ships faster than Germany could sink them. The SS Robert E. Peary's 4-day, 15-hour construction provided dramatic proof. But the real evidence came from sustained production. 3 ships per day in 1943, 2,710 total by war's end. German strategists had calculated that sinking Allied ships faster than construction replaced them would win the war through attrition. They were correct in theory, but catastrophically wrong in practice. They never understood that American industrial capacity was not fixed. It could expand by orders of magnitude in months. They never comprehended that American shipbuilding was not a craft industry limited by skilled labor availability. It was mass production requiring only determination and resources. The examination of Liberty ships by German intelligence officers after their capture revealed vessels built with welding techniques and modular assembly methods German yards had not adopted. The reports described ships constructed in 6 weeks that performed as reliably as vessels requiring 6 months of traditional construction. German naval strategists read these reports with growing comprehension that they had fundamentally miscalculated American industrial potential. The Liberty ship was not brilliantly designed, it was adequately designed for emergency mass production. Those goals simply did not include aesthetic elegance, engineering optimization, or peacetime economic efficiency. And in that single fact lies the entire story of how America won the tonnage war and ensured Allied victory in World War II.